This is JigsawBot 3000, and it may look a bit familiar. We cannot turn back now, let's keep going. Yeah! Chances are you've seen Jigsaw, the legendary jigsaw-solving robot built by Mark Rober and his team. Or maybe the version Shane built on Stuff Made Here. When I watched these videos over a year ago, I said to myself, one day I'm going to build that too. But entirely out of Lego. However, that may be impossible, because where an actual machine uses precise stepper or servo motors, I use this. Look at that, there's like 5 degrees of slack there. And where they use sensors that can literally sense a human hair split into 50 pieces, I use this. That's massive. This means we need to create a base that squeezes every last bit of precision out of Lego, because we cannot afford any additional slack. Luckily, using some editing magic, we have this base. Now, in order to pick and place pieces across the board, we need some moving mechanisms along the sides. One piece I've been using a lot for this is this Lego screw piece that we could place along the entire y-axis. However, we need quite a lot of them in order to span the entire y-axis. And if you look at it like this, that's a lot of bending and that's not ideal for precision, so this is off the table. I mean, it's on the table, but it's off the table. Instead, let's use gear racks. I made sure to have the mechanisms completely surround the gear racks to avoid any skipping teeth. Furthermore, in order to reduce friction, someone in my live chat suggested I could use little wheels. So I added them. The carriages now move smoothly across the y-axis, but we do need to add some motors. So I'm thinking we could connect a motor like this and connect it with some gears, and maybe then we make this a little bit taller. Yeah, let's take this off and replace these axles. 1 and 2, and then we use a bigger frame piece and then somehow connect this little guy inside of this, like so. We can rotate this little axle in order to move this. So I did a quick build to attach a motor to the gears, but for some reason this motor decided today is a very good day to stop working. That's another motor broken. I don't know what happened. Like, quick test if it's really the motor. Yeah, so this does work, although I'm going to make some guards, because this is very bad. What actually ended up happening is I took it apart to rebuild it entirely, reducing the amount of play there was, making it a lot better, only to then take it apart and rebuild it entirely again. Now this I'm very satisfied with. It does not move around at all and it is still very smooth. So next up I'll quickly copy it over to the other side and then get started on the x-axis. But maybe it would be nice to know what kind of mechanism we're moving around on this axis to pick up the pieces. Because a simple grabbing mechanism like this would be nearly impossible. So let's use pneumatics instead, that I don't have. So I bought this Lego set and it's bigger than I expected. I can't wait for the comments on that one, but it has the Lego pneumatic functions, which is exactly what I need. Although it would be a shame to buy a Lego set and not build it. So this really is quite a lot. And with that, it should be complete. It has turned evening, so I'm going to bed and I will continue tomorrow. Note to future me editing this video, do something cool, make an animation or something, like make something happen. Wow, that was beautiful. I hope. Let's continue building. So now the reason I bought this set. I really like this set. I've never had a pneumatic set before, so it's really cool to see how everything works and you can learn from this, which is really nice. But I do need this Lego piece, so let's take everything apart again. It was fun though while it lasted, which wasn't very long. But yeah, let's get started. So this is the vital piece we need. Similar to what Mark and Shane did, we can connect a tiny suction cup to the cylinder using some hosing. This should create an airtight seal, so when we press it down and press the cylinder down, we can pick up pieces, like that. The only thing we need for this is an actual puzzle. I definitely want an all-white puzzle, just like Mark Rober, but I think 1000 pieces is a bit overkill. So let's go with 100. However, when I went online to find one with unique pieces, it turned out they don't exist. So I tried 3D printing my own puzzle pieces, but the surface was a bit too rough to form an airtight seal. I actually 3D printed these pieces over a year ago, but I just kind of came to a stop as I didn't see any better alternative at the time. That's until I received an email from PCBWay, the sponsor of this video. I sent them my custom puzzle model, and after getting some recommendations from their engineers, they quickly printed my model out of a smooth resin. Sometime later, I received this box. Now this puzzle is exactly what I need, with the unique pieces and smooth finish. This isn't the only service they provide though, as they also create custom PCBs, provide milling surfaces, and have printers that pretty much print every 3D printable material from plastics to metals. Head down to the description to level up your next project, and thank you PCBWay for sponsoring this video. So now that we have an actual puzzle, let's take a closer look at the mechanisms that come with picking and placing. Since we need to be able to rotate the pieces, the suction cup needs to be on a little turntable. I thought we could use something like this, with a little gear to move it around. Then we can connect the suction cup to the turntable so that we can easily rotate it. Finally, we'll add this motor to drive the entire mechanism. This isn't the only thing we need to fit in though, as we also need some way to detect if pieces are placed on top of one another. My initial idea was to have some sort of swiveling mechanism, but it wasn't strong enough to press the button and it was generally just very unstable. So over the course of many hours, I designed a new mechanism that relies on linear motion and the color sensor to detect height differences. This doesn't add any additional forces on the suction cup and is still very detectable. Next up, I connected both sides with some beams to form the x-axis, and I gave the phone a permanent place on the moving head. With some extra reinforcements and quick tests, this is looking very promising. However, we're not done yet. We did fit 4 different components in this head, but we do need a few more. For one, we still need to motorize the x-axis. I don't know how I want to do it in the video. I think the next shot we cut to is going to have the mechanism done. Wow, what an incredible prediction. This moves now, so there you go. I also ordered these large tiles so that we can have a smooth surface to scan and solve the puzzle on. Wait, I've always wanted to do one of these. Sick. So all that is left to do now is fixing up the last few bits. I mounted a motor to pull the cylinder in and out, creating a vacuum. Besides, I had to connect the Mindstorms computers and all of the cables, cause this machine will not work without any controllers. This was nothing I couldn't handle though, so with a few finishing touches, this machine is now done. Wait, hold on. We can't just say this machine is done without even having coded it. Will it actually work? Well, no, it turns out. I spent about a week trying to code something to reliably scan the puzzle pieces, and here's what I found out. Taking like 25 pictures of the board with close-ups of all the pieces is actually not that favorable. For one, because you are so close to the board, you use a very wide angle, making the sides of the pieces along the edges clearly visible, which will mess with the edge matching later on. Secondly, this scanning can take multiple minutes, giving you images that still need to be translated to the full world coordinates. And this is the real deal breaker. I've tried stitching together all of the images to form one large image so that we can easily determine global coordinates. But oh, turns out they might not magically line up with one another. At this point, I was already compensating for things like motor slack, the FOV of the camera, the deltas in terms of distance for the camera and the suction cup, etc. So I tried compensating for any camera distortion too using these calibration papers, but without having them at a fixed place inside of the machine, this isn't going to work. I considered adding a permanent Lego calibration grid to the machine. However, after having a thorough conversation with an expert called my dad, we came to the conclusion that we can solve all of these problems by changing one single thing. And that is the thing I've avoided doing in all of my videos so far. See, if we take the camera off the moving carriage and position it above the field, we can capture all the pieces at once, eliminating the need for stitching together all of the pictures. If we move it even higher, we even eliminate some of the perspective problems because our FOV is now more parallel. So what have I avoided doing in all of my videos so far? Well, I'm basically going to have to rebuild this entire machine, which also means that all of the coding I have done goes out the window. Yeah, losing this much progress doesn't feel great. But hey, at least we've learned something. The reason I didn't do this in the first place is because I was afraid that I wouldn't have a high enough resolution to solve the puzzle, but I have found some solutions that I will get to later. This is one of the first times where I'm actually doubting if I can finish a project, but we cannot turn back now, let's keep going. To keep it short, I started out by completely rebuilding and redesigning the x-axis. Twice, actually, after which I rebuilt the entire base and y-axis from scratch to make them bigger, leaving more space to lay out the pieces. And then actually this is all finished and all we need to do is attach the phone somehow. I still forgot the time-lapse. All of this is not filmed. And then, with a few cables and final finishing touches, the new and improved machine is now done. Hold on, no, of course it's not done. Why would it be done? Apparently, when I rebuilt this base, I didn't make it just large enough. So when the machine goes to pick up some pieces along the edges, they get stuck under some Lego and fall straight back down. This means I'm gonna have to make the machine 2 studs wider. That's it. But that means taking everything apart. Why? Why did I have to build this jigsaw machine? Like, I could have built something simple, like a 3D printer, I don't know, but I had to make a jigsaw machine. And now I'm gonna have to rebuild it again. Wow. Okay, we've been over this before, you know the drill. For real this time, after completely rebuilding the machine, for the 3rd time to be exact, the Jigsaw Bot 3000 is now done. Although this feels great, we're not done yet. And actually I thought I was done today, so I went ahead to film the final showcase, but it turns out it still doesn't work. So let's look at what we have already, and then I'll do some more bug fixing later, and hopefully it actually works by the end of this video. You know what the hardest part was? Getting all of the coordinates to agree with each other. The camera sees the puzzle pieces in its own 2D system in pixels, but every piece also has a real-world position measured in millimeters. It also has a position relative to every other piece and to the camera. And the bigger? That one lives in millimeters to the camera, but in motor degrees to the bed. The bed itself is in millimeters relative to the puzzle pieces, cause why not? On top of that, we rotate the pieces using the gripper in motor degrees, which naturally completely changes their orientation every time. So every time a piece turns, we must recalculate where it is and where it goes across all the coordinate frames and across all mismatched units. See how this gets out of hand fast? So let's just go over the algorithm step by step, as we haven't even talked about things like extracting the pieces and solving the puzzle. I'm actually very excited about this, because I think you're actually gonna learn something, whether you're experienced or not. I'd really like to go a bit in depth here, okay? In my earlier projects, I used DroidCam, which streams real-time video from my phone to the laptop, but at a lower quality. Now I switch to IP webcam, which lets me remotely take a 4K picture instead and send that to the laptop. This transfer just takes a bit longer, but it's barely even noticeable, and we only need one picture anyway. If we were to use this image directly though, it's never going to work, since the camera will be in different positions every time we take a picture. So we use our knowledge of the real world to calibrate it. We can select these 4 corners using this handy interface, and since we know what size and shape they're supposed to be, we transform the image to get a normalized image, independent of the camera position. Then we say all of the white pixels are puzzle pieces and all of the black pixels are background, and we filter out any white blobs that are definitely not puzzle pieces using some standard image processing techniques. Now the part that I'm most proud of, because it's my own solution to a very big problem that As far as I'm aware of, no one else has solved this way. See, before I mentioned that the sides of the puzzle pieces are visible in the thresholded image, and it turns out that we can actually estimate what the image would have looked like if there was no perspective. See, the only sides that are visible are the sides facing the center of the image, and the amount they are visible is determined by the distance to the center of the image. So, if we grab all sides that are facing towards the center and move them away from the center based on how close they are to the center, we end up with an image that closely resembles just the top surfaces of the puzzle pieces. Come on then, focus. Get your head in the game. Thank you. So now we need to interpret the pieces. Hey Dave, how do we extract the valuable information from the thresholded image?
First, we select all possible corners from each piece, by simplifying it until there are only a few points left. Then, we filter these corners based on the bisect. If the bisect points towards the center of the puzzle piece, we know it is very likely one of the outer corners. Together with some other heuristics, we determine the 4 corners that are most likely the outer corners. Finally, we divide the contours in 4 parts, at these corners, which become our 4 puzzle piece sides.
Yeah, that actually makes a lot of sense, thank you. Great, so now we have information about all of the 400 sides of the puzzle pieces. All we need to do now is compare every single side to every other compatible side and find the best matches. In short, we do this by overlaying 2 sides and finding the size of the surface that is created. The smaller the surface is, the better the match. We store all of these results for every single side. This creates a kind of search tree, which we can then use to solve the puzzle using an algorithm called beam search. I won't explain how that works in detail right now, but basically we travel around our puzzle in a spiraling path and we try the best couple of matches for every new piece we add. Then we just keep the best couple of solutions until we are left with only one solution, the actual solution. So that's how we do it, a series of image manipulations followed by mathematical comparisons topped off with a search algorithm. And I cannot even explain how I felt once I got the code to finally solve the puzzle for the first time. So here's my actual reaction. This one should be 12. Look at that, it is 12. Let's see, this one should be piece 14, and it is piece 14. I don't know if you can see this, but it's piece 14. Goes over there, no problem. Oh no, I just messed it up. Well, I guess we're back to solving the puzzle. Yeah, that's right, because we still need to assemble the puzzle. Luckily, this is more straightforward. Is what I would say if I was stupid. And what I did say when I was stupid. Assembling the puzzle caused me to go into many rabbit holes, from finding the most accurate picking and placing coordinates to finding the optimal wiggle routine. Here, just an example. We need to know if we accidentally place a piece on top of another one, so that we can try to place it again. We measure this by the amount we move down until the sensor gets triggered. But since we're working with Lego, it turns out that we need to move further down on the left side of the field compared to the middle of the field, because these simple plastic Lego bricks sag down. This means we need to take measurements at the left, middle and right of the field and fit a polynomial to these 3 points, so that we can dynamically calculate a compensation angle based on the current X position that we need to add to our threshold angles so that we don't accidentally place a piece where it cannot be placed. And this is just one small example, there were many more. I have said I should have never even started this project many times during this process, but I simply had started it, so I didn't want to turn back now. It was just one challenge after the other, and yet you eventually run out of problems to solve. With every test you perform and every mistake you make, you learn something new and you try it again, but better, until you end up with something like this. Running the code and go straight to calibrating the robot. We're going to put a point here, here, here and here. Calibrate. That's looking a lot better. And let's go to start process. Now we're going to extract all of the pieces. I just love the way this looks. All the corners are detected and the sides are removed. All of the pieces are detected, so let's go to matching the sides, which is really quick. We can go ahead and compare them, but I'm not gonna do that. Look at this looks great. So we're gonna solve the puzzle. Oh, this is just so cool to me. Like, it goes round and you see the board change sometimes and it finds the best solution. It looks like this board is solved. So look at that, all these numbers represent where the actual pieces need to be. So all we need to do now is start this robot. 3 left. 2, 1. Perfect. I literally cannot believe that this actually worked. I cannot believe this actually worked. Let's go! Yeah! This has been such a fun project to work on, and the code will be available in the description for you to download. Thank you to everyone who joined live to see me build this machine. Oh, and please just share this video if you thought it was cool. It would help out a lot. Or leave a comment, whatever. Thank you for watching.